For the fourth case of the integration of rational functions by the use of partial fractions, so we have this form. So here, our denominator can be factored into linear and quadratic factors, and some of these quadratic factors are repeated. For example, this one. So as you can see, there is a quadratic factor in its denominator which is repeated twice. So to solve this, we do the same process, or we do the same logic when a linear factor is repeated. So when we do the partial fraction, if the linear factor is repeated, so we just break our linear factor into k components if it is repeated k times. So in this case, if a quadratic factor is repeated k times, so we just decompose it into k components. So here, our k is 2, since it's repeated twice, so we're going to break this quadratic factor into 2 components. First, we have a component for the linear factor and 2 components for our quadratic factor. So one for the denominator x squared plus 2x plus 2, and the other one for x squared plus 2x plus 2 quantity square. So again, for the quadratic factors, its numerator is a linear expression. So by the use of LCD, we have this equation, that is, this numerator in our rational expression is equal to this form. So this requires a very long process to solve for these coefficients a1, a2, b2, a4, a5. So I'm going to give you the values directly. For a1, you have -1, a2 is 1, b2 is 3, a3 is -2, b3 is -3. So we substitute these values in our components, so therefore our integral, or the given integral, is just equal to this form. So you have the integral of -dx over x plus 1 plus the integral of x plus 3 dx over x squared plus 2x plus 2 plus the integral of -2x minus 3 dx over x squared plus 2x plus 2 quantity square. The first one can be solved by ln. So your integral of -dx over x plus 1 is just equal to -ln of the absolute value of x plus 1 plus c. For the second one, we have to employ completing the square and then do some substitution. So by completing the square, your x squared plus 2x plus 2 is just equal to the quantity square of x plus 1 plus 1. So we let y be equal to x plus 1, so we differentiate both sides. So therefore, your dy is just equal to dx. This means our dx here will be replaced with dy, and our x here will be replaced with y minus 1. We just move 1 here to the left side so that we have a value for x. And then for the denominator x squared plus 2x plus 2, this will become y squared plus 1. So therefore, after we substitute this form, we have the integral of your x plus 3 dx over x squared plus 2x plus 2 is just equal to the integral of y plus 2 dy all over y squared plus 1, which we can break into 2 integrals. So the first one is the integral of y dy over y squared plus 1. The other is plus 2 times the integral of dy over y squared plus 1. The first integral can be solved by substitution, which will lead to ln, and the other one can be solved by arctan. Therefore, the integral of this is just equal to 1/2 ln of the absolute value of x squared plus 2x plus 2 plus the integral of the second one is 2 arctan of x plus 1 plus c. We proceed to the third one. So we just use the same substitution here in 2. So in 2, we just use the completing the square and do the substitutions. So we apply the same substitution. So that is for x, we apply y minus 1. For dx, this is replaced by dy. And the denominator will become y squared plus 1 quantity square. Okay, so we can decompose this integral into 2 parts. We have the integral of -2y dy all over y squared plus 1 quantity square. The other is the integral of -dy over y squared plus 1 quantity square. The first one can be solved by simple substitution. So therefore, your integral of negative 2y dy over y squared plus 1 quantity square is just equal to the integral of negative du all over u squared after some substitution, which is just equal to 1 over the x squared plus 2x plus 2 plus c. So we just apply the power rule for anti-differentiation. Now for the last one, which is the integral of negative dy over y squared plus 1 quantity square, we have to do the trigonometric substitution. That is, we use the tan and the secant. So here we equate y to tan theta. So differentiate both sides. That means your dy is secant square theta d theta. So here your dy will be replaced with secant square theta d theta. Now for the square root of y squared plus 1, we equate this with secant theta. So if we raise both sides to a power of 4, we get this equation, that is your secant to the 4 theta is just equal to your y squared plus 1 quantity square. So therefore, the denominator here will be replaced with secant to the 4 theta. So therefore, our integral is just equal to the negative of the integral of secant squared d theta over secant to the 4 theta. So we simplify this form and we get negative of the integral of cosine squared theta d theta, which is just equal to this form. So here we apply the half angle formula. So we recall our trigonometric integrals. So if you want to know how did we arrive here from here before this half angle formula, so take note, we can cancel this and we have secant square in the denominator. So take note, your 1 over secant square is just equal to cosine square. So we recall our trigonometric identities. So therefore, we have negative of the integral of cosine squared theta d theta. So this is a trigonometric integral which can be solved by the second case for cosine and sine. So the second case, if we have an even exponent in cosine, so we can express our cosine using this half angle formula. And then we can break this integral into two parts. So we have the integral of 1/2 d theta and the integral of cosine 2 theta over 2 d theta, which is equal to negative 1/2 theta minus 1/4 2 sine theta cosine theta. So all in all, the integral is negative 1/2 arctan of x plus 1 minus the integral of x plus 1 all over 2 times x squared plus 2x plus 2 plus c. So if you notice, how did we get this arctan here and this form? So we just use the substitution for theta here in our trigonometric substitution. So theta here is equal to arctan of x plus 1, and your sine theta here times cosine theta. So we use the substitution for sine theta and cosine theta. So if we draw the right triangle here in our trigonometric substitution, we have, if this is theta, this is y, this is 1, and this is square root of y squared plus 1. So this means your sine theta here, which is equal to the opposite over the hypotenuse, and our cosine theta here is just equal to your adjacent over the hypotenuse. So we multiply these two values. So that is how we get this expression. Okay, so if we multiply these two, you have y over the square root of y squared plus 1 times 1 over the square root of y squared plus 1. So you have y times 1, that is y. Multiply these two, so the square root will be eliminated. So you have y squared plus 1 as the result. So we change y to its original form, which is x plus 1. And your y squared plus 1, the original form is x squared plus 2x plus 2. So we have this result. So all in all, we combine all the integrals. So the integral of our given expression is just equal to, first we have the negative ln of x plus 1, or the absolute value of x plus 1 plus 1/2 ln of the absolute value of x squared plus 2x plus 2 plus 3/2 arctan of x plus 1 minus x minus 1 all over x squared plus 2x plus 2 plus c.